You're going.
Alright, so my demonstration was the iodine clock reaction. Basically, let me start from the top. Why don't you switch this over to these? Okay. Okay, iodine clock reaction. Now this reaction involves chemical kinetics. As you can see the definition I put up there, the study of rates of chemical processes and reactions, right? And so I'll start off with a question. What factors affect reaction rates? Any ideas?
Catalyst.
Catalyst, okay.
The amount.
The amount of
The catalyst.
okay, and what other amounts?
The product and reactants.
Okay, products and reactants, concentrated products and reactants. What else?
Temperature.
Temperature, so physical
pH.
state.
Volume.
Okay, and then are all reaction rates going to be the same for every single type of reaction, or are they going to vary?
Could vary.
Okay, so it depends on what type of reaction it is. It's going to be specific to that reaction, right?
Yes.
So I have them here. Physical conditions, temperature and pressure, concentration of reactive products. You got them all right. You're amazing students. Catalyst, specific reaction that is occurring. All right, and in society there are many uses and applications for kinetics, chemical kinetics. Obviously, it's for reducing the time to yield a product, and that by therefore increasing the yield and you manipulate temperature and pressure and other variables to maximize the yield, reduce the time it takes for the reaction to go through, which will reduce the cost, reduce the effects like environmental impacts and such. And one example I put up there was the Haber-Bosch process. It's like the industrial applications, taking nitrogen gas and hydrogen gas, forming ammonia. And this is this reaction alone is responsible for the fertilizer generated through this ammonia is responsible for sustaining a third of the Earth's population, through agriculture, which is pretty crazy. So, yay kinetics. All right. So for this reaction, these are the reaction mechanisms, which are kind of like the elementary reaction steps for the whole process. And now this isn't there's another version of this iodine clock reaction that's like an oscillating reaction, which has 25 more steps. This is the simpler version. So based off of this, and I have an illustration here because it might not make sense for all the non-chemistry people. That's kind of what it looks like. So you got beaker A, B, and C, and those are the initial chemicals that are going to be present. I didn't put the quantities just to make it simple. But the percentages that you're going to have are going to be water, 61.4%, and these are, obviously you can scale it to however much you want it. Of A, which is potassium iodide, and water is going to be 10%. B is sodium sulfide of water, and C is soluble starch, sulfuric acid, and water. Now if you combine all three of these together, what do you think is going to happen? Any guesses?
An exothermic reaction.
Okay, that's one guess. And any other ideas? I'm not
Clock.
saying you're wrong or right. Make a clock?
Yeah.
What do you mean by that?
I don't know. It's called the iodine clock reaction, so something has to tie in there.
It'll
Okay.
react.
Is it gonna happen in 60 seconds?
Ugh.
Or it's like a clock?
It'll be it'll tick. It'll tick.
Perhaps? Okay. Well, those are some ideas. I'm going to move over to this guy.
That'd be the coolest thing ever.
Okay. So basically, in this beaker here, I have solutions A and C already combined. Solution B is in this graduated cylinder, and I'm about to combine it, and we'll find out what happens. Hey. Or is it?
I'm so nervous.
When you do this demonstration for your class, you can vary the amounts to get different effects, but I'm not spoiling anything for now. This side. Whoa! And all of a sudden. Okay. So moving back to this side.
Yeah. I thought it was going to gradually change colors.
No, that's
So what is going on here? So you got the combination. This was in the beaker. I've highlighted in colors, right, the ions that form after combining those. So you have the starch that's going to be in the reaction. You have the iodide that's going to be in the reaction. the proton from the sulfuric acid is going to react, and then the hydrogen sulfide. So now you see this reaction occurs in these steps here, right? So you'll have these precursor ions that are here, and they'll form this product, iodine. And then that accumulates over here and is used to create iodine, I2. Now this process is really slow. So it's using all these products here, creating iodine. The problem is this third guy is really, really fast. So as soon as this iodine forms, this reaction takes it away. So essentially, as long as there is hydrogen sulfide remaining in this total solution, this iodine is not going to exist. It's going to keep taking it away, turning it into iodine, right? This ion here. Until he runs out. And then if he runs out, what's going to happen with this iodine? It's going to be made here, but it's not going to be taken away here, so it's going to start to accumulate. And do we have enough iodine ions? Yes, we do, with tons of it. So as soon as this guy starts to accumulate, it combines with this starch, and this reaction, there's still not much known about it, of how it reacts, but these guys form a complex. It's called a starch-iodine complex. And this complex has that blue, black, dark black color. And so that's the reasoning behind that. That's why you get this kind of delay, and then suddenly it turns black. And now there are alternative forms of this. This one here. Now this one is called the Briggs-Rauscher version of that, and this one's called the oscillating clock because it oscillates, obviously. And this one includes like malonic acid, manganese sulfate, hydrogen peroxide. And basically what it does is one reaction creates these products, and the products of this are like another color. So it keeps oscillating back and forth, but the concept is still the same. Until that one guy, that fast reaction, that once that runs out, the reaction finally stops, but it'll oscillate, which is another cool demo that you could do for your students. Oh, you are students, but if you become teachers one day. So the amber color is iodine, I2, and then switches over to the starch complex. And I'll switch back, and the clear colorless is iodine to ion, anion. So just keep flipping back and forth. And the two guys that actually found this, it was actually initially discovered by this Russian guy. And he put it on some obscure science journal, and these two science teachers, high school science teachers in San Francisco found it, and then they discovered this. And so that's pretty cool. Just a bunch of teachers that figured it out. Alright, well, pretty much does that until it winds down and ends. In terms of safety, most of the chemicals are safe. Sulfuric acid obviously is corrosive. You want to keep that stored safely and away, locked away. And the potassium iodine, it could be combustible, so you want to keep it away from heat. But other than that, they're generally safe for lab use. And that is it.